Today we're going to take a look at section 9.5, which is alternating series. We're also going to talk in this section about something called absolute and conditional convergence. Our first thing that we're going to take a look at is theorem 9.14, which talks about alternating series, and it says the following. Let a sub n be greater than or equal to 0. The alternating series the summation from n equal 1 to infinity of negative 1 to the n times a sub n converges when number 1, so I have two conditions actually. Number 1, the limit of the part that's not going to be alternating, not the negative 1 part, so the limit of a sub n is 0. And secondly, a sub n plus 1 is less than or equal to a sub n for all n. So this is basically saying that the sequence is decreasing. Okay, so if we have those two conditions met, then our alternating series will actually converge. Now, there's a catch to that. We've seen this whole limit business here before, and we know that finding the limit of just the sequence does not necessarily mean that the series converges, right? We saw that with the harmonic series. But for alternating series, it's actually sufficient to actually prove that, along, of course, with the second condition that's here. So we're going to do a couple of examples for this. We are going to determine the convergence or the divergence of the series. And the first one that we're going to take a look at, we're going to do a couple of these, is going to be the summation from n equal 1 to infinity of negative 1 times n squared over n plus 1. All right, so we have to verify two things to know whether or not this converges. We have to verify that the sequence is decreasing, and then we also have to verify, secondly, the sequence decreasing actually is number 2, but we have to verify that we actually have a limit of the portion that's not the alternating part, i.e. this one, that's 0. So we're going to start with that one. That one's actually listed first as the item to check. So we're going to do our limit as n goes to infinity of n squared over n plus 1. This is back in like section 9.1 where we multiply this by 1 over n squared, or you could even multiply by 1 over n here. It works pretty nicely. I'll go with that one here just so you can see what that one looks like. So this would give me the limit as n goes to infinity of n on top. I would have 1 plus 1 over n on bottom. Obviously, you all know that the 1 over n goes to 0, so the denominator is actually just the number 1, the limit of it anyway. And the numerator goes to infinity, so this limit is actually infinity. Clearly, infinity does not equal 0. So it fails, right? So this is a problem. It fails this part, doesn't work. So what does that mean? Well, it means by the alternating series test for divergence, AST, we'll abbreviate it, the summation from n equal 1 to infinity of negative 1 to the n times n squared over n plus 1 diverges. Because it fails one of the two pieces that it needed to pass in order to actually be convergent. Now keep in mind, I don't need to actually check the second condition. It's completely irrelevant. Even if the second condition holds, the first condition didn't. So I'm done if I get one of them to fail. If this one had passed, if it actually showed that it did go to 0, that limit was 0, then I'd have to check the second one as well. So let's do another example, same directions. Summation from n equal 1 to infinity of negative 1 to the n times 2e to the negative n. Okay, again, we have two conditions to check for. The first condition is to decide if the limit as n goes to infinity of 2e to the negative n in fact equals 0. So we have to check that. There's several things that we could do. I'm going to choose to rewrite the expression with positive exponents. In particular, that would look like 2 over e to the n. So as n goes to infinity, what does that look like? Well, actually, I would like to draw you a picture. It's a graph you're familiar with, but we're going to draw the picture of e to the x. And we're going to do it on the positive side, simply because that's the values that we're looking at. Our graph of e to the x looks like this. It crosses here at 1. All right. So this portion, the e to the n portion, goes to infinity. So as n goes to infinity, e to the n goes to infinity. So when we have 2 over something that's going to go to infinity, that limit actually is 0. So our first check step of our alternating series test checks out. Our second check step then is to confirm that it's actually an increasing sequence. So let's take a look at that. All right, and so to check that, we're going to do something that you've seen me do before. We're going to create a ratio of a sub n plus 1 to a sub n. If you want to create the ratio the other direction, that'll be fine too. And I'm going to use the version of this where I had positive exponents. So it looks like this for a sub n. All right, so the a sub n, my denominator itself would be 2 over e to the n. Now the numerator would actually be 2 over e to the n plus 1. So we've got a fraction within a fraction. We can definitely clean that up and simplify that. So this would be 2 over, in fact, let me do it over here for the moment and clean it up, a little bit of space here. So I have 2 over n plus 1. I'm sorry, e to the n plus 1. My bad. And I would be multiplying that by the reciprocal, which would be e to the n over 2. Now taking a look at this, remembering order of, or not order, but of properties of exponents, this is actually the same as e to the n times e to the 1. Okay? That's actually a more helpful way of viewing this, because if you take a look, then the e to the n's cancel and the 2's cancel. So this actually leaves me with simply 1 over e. So let's go back to what we have. I have a sub n plus 1 over a sub n equals 1 over e. So let's take a look at what happens. Well, I mean, if I multiply e to the other side, across multiply, I could say it that way. I have e times a sub n plus 1, and that's equal to a sub n. Okay, so there's a couple of different thoughts that I have at this point on how we could sort of go from here. One is to recognize that you know what e is. It's approximately 2.718, right? So what we're saying is that if you took 2.718 times a sub n plus 1, it would equal a sub n, which means that a sub n plus 1 must necessarily be less than strictly actually a sub n. Otherwise, I couldn't multiply it by 2.718 and it actually work. Another way to think about this is I could leave this on the side and then put my a sub n with my 2.718, my e, in this denominator. And if you do that, you're actually dividing a sub n by something that is bigger than 1, which makes it smaller, right? This fraction would be smaller than if you just had a sub n by itself. So it's another way to sort of think about it. Either way, we actually end up with the desired result that we have. We have our second condition met. So by the alternating series test, we know that this series, summation from n equal 1 to infinity, of negative 1 to the n, times 2e to the negative n, converges. All right, so I'd like to maybe develop a little bit of where we're going next and why this is happening with a little bit of a setup. So sometimes a series may have both positive and negative terms. And abbreviate a little bit as we do this. but it doesn't alternate. So let me give you an example. If we had the summation from n equal 1 to infinity of sine of n over n squared. Clearly the denominator is always positive, but sine, as you know, goes between positive 1 and negative 1. And because it's sine of n, and it's not like n pi, it's not going to automatically go between values that are necessarily whole values, like negative 1, positive 1, negative 1, positive 1. It doesn't necessarily do that. It's going to bounce around with positive and negative, sort of irregular listing of numbers. So this actually would look something like what we're talking about. So this has both positive and negative terms. But does not alternate. So one way to gain some information in a situation like this, and we can use what I'm about to show you for other situations where they are alternating as well, but this is kind of the crux of why we've created this alternate option here. So one way to gain some information is to consider what happens when you look at the absolute value of this. So the summation of n equal 1 to infinity of the same a sub n that I just did, so sine of n over n squared, but the absolute value of that instead. By direct comparison, remember that test? We did that a couple days ago. The sine of n over n squared would actually be less than or equal to 1 over n squared, right? Because sine goes between positive 1 and negative 1. We've taken the absolute value, so it's certainly less than or equal to 1. And by the p-series test, we know that the summation from n equal 1 to infinity of 1 over n squared converges. So, since that converges, it automatically means the summation from n equal 1 to infinity of sine of n over n squared converges. So when we do this process where we take this sort of absolute value of our terms instead, and we're only considering the absolute value of the terms, when this actually happens, that this absolute value ends up converging, that is actually called absolute convergence. So this is theorem 9.16, and it's called absolute convergence. And it says the following. If the series the summation of a sub n in absolute values converges, then automatically the summation of a sub n converges. And notice it doesn't say the other way around. It doesn't say that if the summation of a sub n converges, that this absolute value one is going to converge as well. And in fact, it doesn't have to work that way at all. So let me give you a couple of definitions that I've alluded to already. So the first one is this. The summation from n equal 1 to infinity of a sub n is absolutely convergent when the summation of the absolute value of a sub n converges. So when the absolute value of a sub n as a series converges, then we call the series absolutely convergent. And unfortunately, that doesn't always happen. The sum from n equal 1 to infinity of a sub n is considered conditionally convergent. When the summation of a sub n converges but the summation of the absolute value of a sub n diverges. And to show this point, let's do a couple of examples. We're going to determine the convergence or divergence of the series. Okay, and the first one we're going to do, this is example number 3, is the summation from n equal 1 to infinity of negative 1 to the n plus 1 over n squared. All right, so, we could test the absolute convergence first. We can test the conditional convergence first. If we test for absolute convergence and it doesn't converge, then we have to test for conditional convergence. But if we test for conditional convergence and it does converge, we still have to check for absolute convergence. So it's kind of, 6 one way, half a dozen the other. I mean, you're just as likely to pick the one that's going to end up giving you more work as the one that's going to end up giving you less work, because you just don't necessarily know what's going to happen. So I'm going to default to just trying the absolute convergent part first, part 1. And if it, requires, then I'll move on to step 2 and try for conditional convergence. So we'll start by checking for absolute convergence. Okay, so absolute convergence says that I want to figure out what happens to this sequence, the series, when I actually don't have the negative 1 to the n. And yeah, I realize this says negative 1 to the n plus 1. Instead of just saying to the n, it has absolutely no irrelevance. It just doesn't matter. It just means that it starts on the opposite sign than if I'd had a power of n. So it still ends up giving me a sequence of 1 over n squared when I consider only the absolute value of the original sequence. Now, we actually know that this converges. And if you'll remember, it converges by the p-series test. So, according to our definition up here, because the absolute value right here converges, we know for sure that it's absolutely convergent. So the summation from n equal 1 to infinity of negative 1 to the n plus 1 over n squared is absolutely convergent. Okay, so same directions. Let's try another one and see how it goes. Number 4, we're going to do the summation from n equal 1 to infinity of negative 1 to the n over n natural log of n. And again, you could start by testing for the convergence or by testing for, the absolute convergence, or by testing for the conditional convergence and simply go from there. Just so that I'm always, sort of testing things in the same order, I'm going to test for absolute convergence first. Okay, so this is the one that I'm choosing to start with. You can start with the other one if you'd like. So I want to know what happens when I but when I'm only looking at this from an absolute value perspective, which means that the numerator does not affect anything. And I just have n natural log of n in my denominator. Now when I see that 1 over n natural log of n, to me it sort of just screams integral test. Because I have a natural log and I have an n right beside it in the denominator. So in particular, if I did the integral from 1 to infinity of 1 over, and I'll change it into x's for the sake of it looking more like we were used to seeing, and it kind of looks weird still because I have so many n's in there with the natural log. So I have 1 over x ln x dx, of course. And I can do u substitution. My u would be natural log of x, and my du would be 1 over x dx. So when this is rewritten, and I'll leave off the limits for the moment since I'm working in terms of u, I have 1 over u du. And of course, the antiderivative of 1 over u is natural log of u. And I'm trying to evaluate at something that's for x's, and right now this is in u's. So in terms of x's, this is the natural log, and u is the natural log of x. This is natural log of the natural log of x. But it needs to be evaluated that 1 and infinity I had before. So this is 1 and it's n because we're going to let n go to infinity. So more properly, we're going to let the limit as n goes to infinity of the natural log of the natural log of n minus the natural log of the natural log of 1. All right, so the second part is really not all that important, but it is important to recognize right here that as natural log goes to infinity, as the natural log of n has n going to infinity, this is also going to be infinite. So again, you're going to have another infinite inside of the natural log. This ends up being infinity. So in particular, what we just found out is, yeah, it didn't converge, it diverged, right, by the integral test. So by the integral test, the summation from n equal 1 to infinity of negative 1 to the n over n ln n diverges. Now, all that we know is the absolute value of this, all that we know is that the absolute value diverges. We don't know, which means it's not absolutely convergent. It doesn't tell us anything about conditional convergence. So just because it doesn't absolutely converge doesn't necessarily mean that it can conditionally converge. So now we're going to test, since we know it does not absolutely converge, we're going to test for it to be conditionally convergent. Okay, so this is conditional, before we had absolute. So conditional, what does that look like? Well, the summation from n equal 1 to infinity of negative 1 to the n over n ln n must be considered in its entirety. But you will recognize, of course, that this is an alternating series. And by an alternating series, if the limit of the sequence goes to 0, the sequence part itself, not the whole thing, but the sequence part, then this is going to converge. So that's the part that we're going to look at next. Let me make this a little bit smaller. Okay, so I really need to test using the alternate series test. All right, we're going to test the limit as n goes to infinity, again, of the part that doesn't include the alternating part, but the other portion of it, in natural log of infinity. Well, see, here's the thing. The numerator is 1, so that's cool. And I've got infinity here, because it's n, and n is going to infinity. Oops, this should say natural log of n. Just jumping the gun there. And then this piece over here has the natural log, again, of infinity, so that's infinite. So this whole thing is essentially 1 over something becoming infinitely large, which would make this the value 0. Okay, and that's because n is going to infinity and natural log of n is going to infinity. I mean, that's what's causing that. So what does that mean? Well, it means that the alternating series converges. But the absolute, it was not absolutely convergent, so the summation from n equal 1 to infinity of negative 1 to the n over n ln n converges conditionally. All right, we're going to do one more problem before we call it quits for today. That problem, let me turn my page here, number 5 is the summation from n equal 1 to infinity of negative 1 to the n plus 1 times 2n plus 3 over n plus 10. All right, so again, we can test either thing first. We can test for absolute convergence first or conditional convergence first. So I've been testing for absolute convergence first, so I'll just continue that pattern. So this is for absolute convergence. So to test for absolute convergence, I need to see if the summation from n equal 1 to infinity of the portion that's not the alternating part, right? The 2n plus 3, because it's the absolute value, over n plus 10. And I want to find this particular series, is it convergent or divergent? Well, as we've talked about in class, if you're really looking at this 2n plus 3 over n plus 10, the plus 3 and the plus 10 are irrelevant, truthfully. And 2n over n would be 2. So our expectation is that the limit here is 2. And so that's what we'll do next, is we'll actually prove that that's what's happening. So the limit as n goes to infinity of 2n plus 3 over n plus 10, and we would multiply by the 1 over n, which would give me that the limit as n goes to infinity of 2 plus 3 over n over 1 plus 10 over n. And of course, these values both go to 0. So I'm left with a limit of 2. So 2 is a great number. I mean, like, that's fantastic. But if you remember, what we're really looking for when we're looking at the alternating series possibility, right? What happens here is we still have to have our sequence going to 0, and this sequence approaches 2. So that's not good. So the summation from n equal 1 to infinity of 2n plus 3 over n plus 10 diverges. And it diverges by the nth term divergence test. Okay, but again, just because it doesn't, so what that actually tells us is that the sum from n equal 1 to infinity of the absolute value of -1 to the n times 2n plus 3, actually n plus 1, of 2n plus 3 over n plus 10. And as I look at this, I know that this is not absolutely convergent, because when I took absolute values, it didn't converge. So absolute convergence didn't work, so now we're going to test for conditional convergence. And for conditional convergence, we actually want to take a look at the series itself that we were given, this piece right here. And, oops, sorry, that's not it. We'll go up a little bit further. This right here. And we're going to recognize that this is an alternating series test, right? It's an alternating series anyway. So consider the alternating series test for the summation from n equal 1 to infinity of -1 to the n plus 1 times 2n plus 3 divided by n plus 10. Okay, so this is an alternating series test. So if it's an alternating series test, it will converge if the limit as n goes to infinity of all the parts that are not the infinity, or not the -1 to the n part, but all the rest of it actually does something specific. So we're going to do the limit as n goes to infinity of 2n plus 3 over n plus 10. And it starts to look awfully familiar. We just did this a minute ago, right? We multiply by 1 over n, and we find out, after doing all this, that the limit as n goes to infinity of 2 plus 3 over n over 1 plus 10 over n. These go to 0. So all in all, this ends up being a 2/1 ratio, right? But it's a problem. This is not 0, right? It's not 0. So by the alternating series test, the summation from n equal 1 to infinity of -1 to the n plus 1 times 2n plus 3 over n plus 10 will diverge. Hence, it's not conditionally convergent. Okay, that's all I have for you today. Well, that's not exactly true. I have homework for you as well, so I'm going to flip to the next screen to write the homework down. Your homework, there's a web assigned homework too, so make sure you check that out. But your homework is on page 625, and it's the following numbers: 6, 9, 12, 15, 18, 21, and then I have 37, 40, 43, 46, and 49. So these are the problems to take a look at from this section.